Hi, my name is Ryan Thompson, and this is my Assignment 5 midterm review for CPSC 5210. So question 1 of 5. Show that t of n is equal to t n minus 1 plus n is bounded by big O n squared. We'll do this proof by using substitution. T of n less than or equal to c n minus 1 squared. So this is your constant. So this is the basic construct for what this is the upper bound. So expanding this full form, you have c n minus 1 squared expands to n squared minus 2n plus 1 plus n. This is your f of n. This with the c carried through is c n squared minus 2cn plus c plus n. So how can we bound this term to get back to n squared? Well, since 2cn is greater than c plus n, you can take that term away because this is actually a negative term. So this is such a large term, it overpowers the constant term plus n. So c of n squared is greater than or equal to this full term. For c greater than or equal to 1. Because if c were less than 1 or c was 0, then this would be an addition and that would create a new upper bound. So as long as c is greater than or equal to 1, this term will exist and it will overpower this term, and this inequality will hold. So c n squared can be the upper bound for this total time of the algorithm. Question 2 of 5. T of n is equal to 2t n divided by 4 plus n squared. Use master theorem to find the asymptotically tight bounds. Well, given the form a t of n divided by b plus f of n, that's our basic starting form for the master theorem. So a is 2, b is 4, and f of n is n squared. Here I've defined those terms. Then we can have a functional form to evaluate n raised to log b a. And b again in this case is 4, a is 2. So this is equal to n raised to the 1/2. Now f of n divided by n log b, which is 4, to 2, which is a, is equal to n squared over n to the 1/2. Then there exists an n raised to epsilon such that epsilon greater than 0 allows this functional form n log b of a plus epsilon to equal f of n. And this is case 3, or omega, which is our lower bound. And following the master theorem, theta is now f of n, which is equal to theta n squared. So this is how the master theorem gives the asymptotically tight bounds for this total runtime equation. Question 3 of 5. Give 2 examples when the master theorem cases do not apply to solving the bounded cases for a total time. Example 1. Here, total time is equal to 5 t of n plus n squared. A, again, we always have the functional form a t of n divided by b plus f of n. Here, a is equal to 5, b would be equal to 1, but that stops our case. Our initial assumption is violated because b must be greater than 1. But here b is equal to 1, so the master theorem does not apply, does not work. These cases do not apply to this runtime equation. Example 2. T of n is equal to 2t n divided by 2 plus n log n. So we have another ratio that we can evaluate, which is f of n divided by n raised log 2 to log b of a. Substituting the f of n here in log n and substituting b and a into that equation, that ratio works out to n log n over n, which reduces down to log n. But log n is not polynomially bounded by n, and that means it falls between case 2 and 3. Case 2 is when these two are equal right off the bat, and case 3 is when you have an epsilon greater than 0, such that you can add that epsilon back in to f of n to get it to equal, or so where you can add the epsilon back into n raised log b of a and get it to equal f of n. So it falls between the cases because it can't be 0, but it's also not a number greater than 0. So it falls between two cases, and it does not apply to this master theorem, case 1, 2, or 3. Question 4 of 5. This is an extension of a problem from the random quicksort. Given 3 randomly sampled values of an array A, what is the probability that a resorting of the random sampling will occur following the quicksort algorithm if the middle value is chosen as the partition value? So the middle value or the median value. The number of distinct permutations for n equal to 3, which is the 3 randomly chosen, is 3 factorial or 6 total combinations. So if we let B be an array that's a list of distinct combinations of randomly selected elements of A, then the probability that the median, the middle value of B, is equal to the minimum value of B, 2 over 6, therefore 6 minus 2 over 6 is equal to 4 over 6, or 2/3. So there is a 2/3 chance of a sort being required of 3 randomly selected elements. Now, when I say a sort is required, I'm meaning that you don't have to recursively move elements. In the quicksort algorithm, when you get to the last step, the last line in the problem, you will still have to take A of R and replace it with A of I plus 1. So that step will always be there, and you can't get around it, but you can get around having to recursively sort each one if your partition value is your minimum value to begin with. And I have an example for that. So continued on question 4, here's an example. Let C equal a three-number array that are all elements of A. So C is equal to 8, 4, and 2 of A. And B is the list of possible combinations of C. So B has 1, 2, 3, 4, 5, 6 combinations, as you can see here. Now the minimum value of B is 2, which is also the minimum value of C, and is the middle position for 2 of the 6 combinations. So showing these distinct combinations, you can see combination 1 and combination 2. So when you select this as your partition value, none of these other 2 values are less than or equal to that value, which means that that recursive call doesn't happen. You don't have to go through each element and move it back and forth. You're still evaluating it, but you're still not having to get the overhead time to sort the new element to the element before it. So the probability that the minimum B is equal to the median, the middle value, is 2 combinations of 6 total, which is the total number of combinations where a resorting is not required. Now again, the resorting not required excludes that last line because A of R will go to A of I plus 1 in every single case. So that is not dependent on this random combination that you sample. So the probability that a resort is required is equal to the total probability, so 6 of 6 cases, or 6 minus the probability that the minimum value is also the median value, so this middle value, is equal to 6 minus 2 over 6, which is equal to, reduces down to 2/3. So given 3 random sampling of an element, there's a 2/3 chance that you're going to have to move these indexes before you reach the final value. Question 5 of 5. Given the definition that a stable algorithm is defined by numbers with the same value appear in the output array in the same order as they do the input array. Prove that the counting sort is stable based on the algorithm on page 195. For any indexing of A, the values are monotonically increasing such that the elements of A are numbered 1, which is less than 2, less than ... n, where n is the total number of elements. For each element of C, the value is a cumulative sum of the occurrences such that C of 1 is less than or equal to C of 2, which is less than or equal to C of K, where K is the maximum of A. But only the index values for which C index are elements of A, so are of concern, since any other value will not be used. And I make this distinction because there's always a gap in all of these values where the element may not appear in A. So because K can extend out to a very large range, it may create an index position for a value that is never in A. So we really only concern ourselves with when you have a value of C, when you have an index value of C that's an element of A. Now again, following that algorithm on 195, you would have known that by the last time that C is resorted, C becomes the cumulative sum representing the maximum number of elements at or below a given C. So if you have the maximum value of 5, then at the index 3, that will represent the total number of 3s that occur. So that if the total number of 3 occurs is 4, there's 4 or less values equal to 3, including any repeating digits of 3, obviously. Then after each time CI is called, so after that third index is called, it's decremented by 1. And the index value for A is also lowered by 1. Because again, following that algorithm, you're starting at the very last index of A and working your way down. So you're starting at the seemingly the last occurrence. You're starting at the last occurrence of A. The original occurrence of numbers with the same value will maintain their position relative to each other. So C of A of J is not equal to C of A of J minus 1, because even if A of J is 3 and A of J minus 1 is 3, that value, the first time it's called, has been decremented down. And so that way, as the indexing for C decreases, it will never be the same again. So if starting position says there's 4 values at a given index or less, then once C is decremented down, then there's 3 values at or less. So that's how the counting sort is a stable algorithm, because of when you index in, you are looking at the maximum number at or below a given value, and you decrement that down as A starts at the last index and decrements down as well. So because you're keeping this monotonically decreasing order set, you maintain those relative positions. Thank you.